So here we're still in section 3.4, and I wanted to do one more proof where you have to break a proof up into cases. All right, so this proof says, prove the following. For all integers m squared is equal to 5k, or 5k plus 1, or 5k plus 4 for some integer k. Now the difference in this one and the last one is that we can write m squared in 3 different forms. And so we just have to make sure that m squared matches one of those. The other thing that you'll notice is that this is for all integers and not just for odd integers. So now we need to consider every single case that there is. So our aim is to be able to write, this is our conclusion over here, is that we'll be able to write this m squared in one of these forms. And it has to be for some integer k. And then the other thing, the hypothesis part, is the for all integers. All right, so instead of just the odd, we're talking about any integer. And so if we wanted to write this into an if-then kind of format, we could say something like, if m is an element of the integers, then m squared is equal to 5k. M squared is equal to 5k plus 1, or m squared is equal to 5k plus 4, where k is an integer. All right, so that's what we're aiming for here. So let's think about, if I want to use the quotient remainder theorem, all right, so if I'm going to be able to use that, then I want to be able to write m in several different formats. All right, so and we want to make sure we take care of all the cases that are possible. Now the fact that I have a 5 makes me think that, okay, I'm probably going to have to write it as 5 times something plus 1, 5 times something plus 2, and then the very last one would be 5 times something plus 4. Now it might be a little bit confusing because we've got that m squared equals 5 times something plus 1, but this is different than just the plain old m. All right, so I'm going to be writing m as 5 times something, where that something is an integer, and I don't want to use a k, and I don't want to use an m because I already have those. So let's maybe do, how about 5p? All right, so I can write it like this. All right, so we've got really 5 different cases here. So we'll really need to go through and look at each one of these to be able to see if we can make it fit one of these forms that we're given, either the 5k, 5k plus 1, 5k plus 4. So let's go through and actually prove this. All right, so first thing we're going to do, of course, is to assume or let whatever the hypothesis is be true. So we're going to assume that m is an element of the integers. All right, and then we said on the previous page we're going to break this up into the 5 cases, and that's by the quotient remainder theorem. All right, now you can just say the QR theorem if you want. I'm going to say that we have 5 cases. Either m is 5 times p, m equals 5p plus 1, m equals 5p plus 2, m equals 5p plus 3, or m equals 5p plus 4. And of course, in each case, our p is an integer. So let's look at our 5 cases. So let's see, we've got case 1. All right, and this is when m is equal to 5p. All right, well, if in the case where m equals 5p, this is going to imply that m squared is going to be equal to 5p squared. All right, and again, my aim is to rewrite it in terms of one of these that we have up here at the top. And I think you can probably pretty easily see it's going to be the first one, but let's just go through and do it. Here we're going to have a 25p squared. And if I'm aiming to write it as 5 times something, I can certainly write this as 5 times 5p squared. All right, and so now we have 5 times something, and so that k that we were looking at up at the top, our k can be this thing right here, 5p squared. The only thing we need to make sure of is that k is an integer. I think you know that k is an integer by the closure property because all we're doing is multiplying integers, and so we'll just state that. All right, so we'll say by the closure property, five p squared is an integer. And so if we just let k equal 5p squared here, then m squared is equal to 5k, where k is an integer. All right, so that takes care of the first one. The first one, we made it look like this first type that we have up here. So now we just move on to case number 2. All right, and that's where m equals 5p plus 1. All right, well, in the case that you have 5p plus 1, m squared would be 5 times p plus 1 squared. So that's going to be 25p squared plus 10p plus 1. And now we look and say, okay, which type do we have to make it look like? Well, we've got 3 choices up here. I don't think we're going to make it look like 5k, but I do think we can make it look like the second one, 5k plus 1. And so if I just factor out a 5 here, I can get 5 times 5p squared plus 2p plus 1. And so now we see that this is a very similar kind of argument here. I need to figure out what my k is, and my k is going to be what's in parentheses right here. So I just need to argue that what's in the parentheses is indeed an integer. All right, so just like before, we'll say by the closure property, uh, 5p squared plus 2p is an integer. And so if we let k equal 5p squared plus 2p, then m squared is equal to 5 times k plus 1, where k is an integer. All right, and so then we need to do the other 3 cases. All right, so let's look at case 3. All right, here we have 5p plus 2, and so that's going to imply that m squared is equal to 5p plus 2 squared, which is 25p squared, plus a 20p plus 4. And so now we can see that, oh, we're probably going to have to use this last one here because of the 4 that's at the end. All right, so let's write that as 5 times 5p squared plus 4p plus 4. And then you can kind of see the same kind of argument. So the hard part, once you get past the, deciding the cases, the argument kind of falls out very similarly for each one. The only difference is we've got 3 different forms that it could fit, so we have to decide which one. But to be able to determine what kind of cases do I need to start with. All right, and so I think you can see here that we need to have this to be our k. So we need to make the argument that that is indeed an integer. And so we'll say by the closure property. In fact, from up here, I'm going to put ditto marks by the closure property. Let's see, 5p squared plus 4p is an integer. And so if we let k equal that 5p squared plus 4p, then m squared can indeed be written as 5k plus 4, where k is an integer. And so now you would do your case 4 and case 5 in the exact same way. It turns out that in case 4, when you let m equal 5p plus 3, doing a little algebra, you can write it as 5 times something plus 4, and that plus 4 is nice because that means that your m squared is 5k plus 4. Again, you have to make the argument that what's in parentheses, the k, is indeed an integer, and we can say about the closure property that's true, and then just let k equal that, and you've got it. Similarly, case 5, you have m equals 5p plus 4, and we're able to write m squared as 5k plus 1. All right, so there's the full argument there, and you can see that in all the cases, we were able to rewrite m squared in one of these forms that we had up here. All right, so let's make our final conclusion. We'll say, therefore, m squared can be written in the form m squared equals 5k, m squared equals 5k plus 1, or m squared equals 5k plus 4. And of course, that's going to be where k is an integer. All right, and so we're done with this one. That's the very last thing that we needed to show. We needed to write our conclusion, and we were able to do that by writing m squared in one of the forms above.